Welcome back to the Pump Design Lab. In Part 1, pressure-guided fluid through a curved path. Now we will study liquid that rotates continuously around a center. Our first model is forced vortex flow. The easiest way to understand it is to picture a simple glass of water being turned by hand. The rotating glass experiment. Turn a glass of water steadily. At first, the glass wall moves while the water lags behind. But friction between the wall and the liquid gradually drags the water into rotation. After some time, most of the water turns with the glass. The key point is that every radius completes one revolution in the same time. Same angular speed, different linear speed. If every radius completes one revolution together, angular speed is the same everywhere. But the outer liquid travels around a larger circle in that same time. So it has a higher linear or tangential speed. A merry-go-round gives the same picture. A child at the rim moves faster than a child near the center. Forced vortex rule. For forced vortex flow, we write c theta equals omega r. Tangential speed equals angular speed multiplied by radius. At the center, tangential speed is 0. Moving outward, speed rises linearly. Because the outer liquid moves faster, it needs a stronger inward force to remain on its circular path. Why pressure rises outward? The faster outer liquid requires a stronger inward pressure force. Therefore, pressure rises toward the outside radius. The higher outside pressure pushes inward, keeping the liquid rotating in circles. This is the same radial equilibrium principle we saw in a pipe bend, now applied to a rotating liquid. Forced vortex pressure distribution. For an ideal forced vortex, the pressure rise is written as P minus P0 equals half times rho omega 2, R2 minus R0 2. The important message is not memorizing the full equation. It is understanding that pressure rises more strongly as we move outward. The liquid surface makes this result visible. Why the surface becomes a bowl? In an open rotating container, the water surface drops in the middle and rises near the rim. It forms a bowl shape. The liquid rises at the outside because pressure is higher there. This simple experiment gives us a clear visual picture of pressure increasing with radius in rotating flow. Pump connection, the Shroud cavity. Now take this idea inside a centrifugal pump. Behind an impeller shroud, there is often a narrow cavity between the rotating impeller and the stationary casing. The rotating shroud drags nearby liquid into swirl. The flow is not perfectly ideal, but it often has forced-vortex-like behavior. Real cavity flow is mixed. A real pump cavity has stationary walls, leakage paths, balancing holes, and friction. These effects slow and disturb the swirl. So the liquid does not rotate exactly like the water in a perfect spinning glass. Still, the forced vortex model gives a valuable first rule. More swirl means higher pressure toward the outer radius. Swirl creates axial thrust effects. Cavity pressure acts on the surfaces of the impeller. When pressure is higher near the outer radius on one side of the impeller, it contributes to axial force along the shaft. This is why cavity geometry, balancing holes, and sealing arrangements influence axial thrust. A small calculation helps show how large this pressure difference can be. Example: pressure rise in rotating water. Consider rapidly rotating water between a radius of 50 millimeters and 150 millimeters. Even over that small distance, the ideal forced vortex pressure rise can be around 100 kilopascals. The exact value depends on speed, but the lesson is clear. Rotating liquid can create meaningful pressure differences over short radial distances. A different vortex, the bathtub drain. Forced vortex is driven by a rotating wall. Now consider a bathtub drain. Water may rotate slowly far from the drain, but it spins much faster as it approaches the center. This is a different vortex story. To understand it, imagine an ice skater changing their body position. The ice skater analogy. A spinning skater speeds up by pulling their arms inward. The same rotational motion is concentrated at a smaller radius. A free vortex follows this same idea. Instead of being continuously driven by a wall, the liquid approximately conserves angular momentum as it moves inward. Forced vortex, the memory picture. Before moving to the next part, hold this force vortex picture clearly. A rotating wall keeps the liquid turning. Angular speed is the same at all radii. Outer liquid has higher tangential speed, and pressure rises outward. This reference picture will make the opposite free vortex pattern much easier to understand. Why vortex models matter in pumps. Real pump flows are rarely perfect forced or free vortices. They include friction, leakage, turbulence, and changing geometry. But the two models give us clean reference pictures for understanding rotating cavities, inlet swirl, vortex cores, and pressure distribution. The common idea remains that curved motion needs a pressure field. Curved motion still needs pressure. Whether flow turns once through an elbow or circles many times in a vortex, it still requires inward force. In both forced and free vortex flow, pressure rises outward to provide that inward force. The important difference is not the direction of pressure rise, but how velocity changes with radius. The big difference is velocity distribution. In forced vortex flow, tangential velocity is greatest near the outside. In free vortex flow, tangential velocity becomes greatest near the center. This reverse velocity pattern changes the pressure behavior near the core and makes free vortex especially important at pump inlets and suction sumps. Part 2. What to remember. Forced vortex is the spinning glass story. External rotation drives the liquid. Angular speed remains constant, tangential speed increases outward, and pressure rises strongly toward the rim. Next, we will follow the bathtub drain story and learn why a free vortex can create high speed and low pressure near its center. Next, free vortex and inlet swirl. In Part 3, we will explore angular momentum conservation, free vortex pressure, real vortex cores, inlet pre-swirl, and curved channel secondary flow. These ideas will take us directly from the bathtub drain to the impeller eye. End card. Part 2 complete. That is the end of Part 2, forced vortex and rotating flow. In Part 3, we will learn why free vortex speed increases toward the center and why inlet swirl can affect head, efficiency, vibration, and cavitation risk. Subscribe to Pump Design Lab and continue with us.